MRS system. So, Tomáš, please.
Yeah, I'm not sure whether I'll be able to tell everything because there is only a limited amount of time. And since we are like 1.5 hours in Slack, I'll cut it short. So if you have any questions regarding my presentation, right now is the right time. No, I'm joking. Actually, I'll cover the basis of the MRS UAV system, which was used basically in all the activities and experiments and competitions and projects which Martin talked about. So I'll show you what we use to achieve the real-world results, what we use for research, what we use for publishing papers and doing simulations, and what you will also use for the summer school task. But first, disclaimer, the first part of my presentation is about the MRS UAV system for research, so I'll be showing you what's inside and maybe how it can be used for your own experiments, your own publications, your own anything you would do with the system. However, the summer school task, which you'll do during this week, is gonna take place in a container environment, and we have developed a system which is gonna shield you as much as possible from the system, because for you, there is not enough time to learn everything you need about the system. So for this summer school, you'll be shielded as much as possible from the technical details. However, you can still use the system for your own good, for your own development, projects, research, playing, whatever. And the first part of the presentation is about that. So Martin probably talked about how we started in the group, and it all started by a motivation. Oh, my video is not playing. That's not good. No, my video. Okay, are any videos playing? That's the question. No. So give me a minute, I'll fix my videos, and then I'll continue, hopefully. Of course, I have tested this before the presentation, but you never know. Stuff breaks. Okay, so no videos, doesn't matter. So you might have noticed 10 years ago, this guy, Vijay Kumar from Pennsylvania, from University of Pennsylvania, has presented a nice TED talk on drones. He presented a swarm of drones which changed shape and moved around. And this was a motivation for us when we started the MRS, and we said, like, we want to do the same thing, just our way. And they have done it in a lab under Vicon system, which is nowadays, of course, used very much for lab development. But we have wanted to do it outside of the lab, not only because we didn't have that much of a funding to buy our own Vicon system, we don't even have a place to put it here in this old building of the university. But for me personally, it was more interesting to bring the robot outside of the lab and to be able to run it anywhere and to show all of you guys how we can run our robots. If you do it inside of a special room, inside of the university, it's not much of a robotics to me. So we have started our own system, development of our own system on the bench. So some of you might remember how PCBs were designed back in the days. And we have come a long way since 2012. And we've come to possessing a system on an embedded hardware with some microcontrollers, some cameras, and this was pretty good. It was quite capable. This little drone was capable of following a person, flying indoors, outside of GPS system, and basically it can do everything we need it to, but it wasn't enough to continue with that. So if any of you wants to pursue the career of designing your own drone from the ground up, building everything yourself, it's possible, but that's not how we do it anymore, because it's not scalable. I'll skip the video, which doesn't play right now. Yeah, the problem with designing your own system from the ground up using hardware is it's not scalable for development, it's not scalable for teaching and simulations, and in the end, I, as the author of the system, was the only one capable of doing anything with it. So I was needed to do every experiment. I was needed for everyone, basically to give them guidance how I would do that with my own hardware. The problem was it was my own hardware. And of course, simulating your own hardware is difficult. Software in the loop is difficult. The system is hard to maintain because if you need to do an update, you need to do a new PCB update, which of course takes time. And the system in the end wasn't modular enough. Nowadays, we have sensors which connect through USB and Ethernet, and building your own PCB just doesn't support that anymore. But it was quite nice, and I had full control over everything on the drone, but it wasn't enough. We have done some nice research with it. Those are the publications which were spawned by those hardware attempts, but it wasn't enough. Nowadays, we use this platform, which is more common, and probably you have seen it somewhere. In the center of the drone, you have a powerful computer with some normal processor. We use Intel NUC computers with Intel CPU, which can handle any computations you may throw at a drone. And this computer, as a heart of the drone, can connect all the sensors together. You can connect cameras, LiDARs, GPS, wireless sensors, whatever. And this computer can handle most of the calculations for 3D mapping, control, and planning. And it can give commands to an underlying embedded hardware, which handles the fast feedback which is needed for the attitude and attitude rate control of a drone. This board here is Pixhawk. It's one of it's the most used and one of many platforms which can support the hardware of the drone with software for stabilization and control. What I mean is, if you want the drone to be a manually controlled model, like an RC model, you need something like this for the drone to fly. There are many alternatives. This is one of many. This is open source, open hardware. We don't develop it, we just buy it, and it just works most of the time. And we use it to control the lowest level layer of the control system on the drone. And we also use it as a backup solution. So when we fly outdoors, if this high-level computer fails, we still have this embedded hardware which can back us up, and hopefully some safety pilot holding the RC transmitter in the hands can safely land the drone even when the Linux computer just broke. And having a Linux computer on board is very useful because we can have all those nice software running on it. We can use ROS, we can use Python, C++, powerful libraries like OpenCV, and basically anything you can imagine running can run on the drone because it just has a more powerful computer than my own laptop, which is true. So this is an architecture which we use since 2015. Luckily, we were introduced to this by Vijay Kumar and University of Pennsylvania. We are very thankful to them. And they give us a kick and an incentive to change our platform from the embedded hardware to this modular and high-level architecture. Of course, this has its downsides because the computer is a normal computer with normal operating system, and it's not real time. And you don't have that much control of what happens inside because there is a lot of stuff running inside which you just can't control. So it's important to still keep in mind that you should not overuse the computer. Still, every time you need some breathing space, some free CPU, free memory, otherwise the drone will crash. So using the computer, we then run robot operating systems on board. You might have heard of it. It's a very nice framework and middleware which allows us to build powerful modular applications. It allows us to connect the applications together, and it allows us to define an interface between those applications. So if you develop some software, we can connect it on our drone to our system, and we can nicely integrate it. It also offers some additional features and benefits. Basically, it brings stuff which you would probably not like developing, which is logging, visualization, some dynamic reconfigure. It fixed problem with time, so the drone has a sense of what time is it and how time takes. All of those important little technical details are already solved by ROS, and you can just focus on implementing the algorithms rather than dealing with technicalities. So we use ROS, and our system is built using ROS. Currently, in my opinion, this is the best middleware for that. There is gonna be a ROS 2 soon. Some of you might already use it. We didn't find it yet well suited for drones. There are some caveats, so we haven't moved yet, but maybe next year we'll move our system to ROS 2. So ROS is the way, and this is the image of the normal drones control pipeline. You might have seen it in every paper, everywhere. Typically, there is some drone plant, which in our case contains the attitude rate controller on the Pixhawk, and somewhere above there are controllers, reference generators, planners, and so on. These building blocks are typical research food currently. Many groups are developing their own controllers, trackers, planners, mappers. And I'll quickly go through what we have here in our system as those 4 blocks. But keep in mind that the system is not just it's not just the math in the blocks. Of course, that's very important, but it's also the implementation. And there is a huge gap between what you would probably consider enough to run as a test. So we'll take the math and you implement it, and then there is a huge gap between what we need to do to make it actually feasible to run repeatedly in conditions which you might not have foreseen, such that the drone will fly every time. And I'll briefly touch it. So, for example, you might have heard about linear Kalman filter, a traditional filtering method, which in MATLAB is like 10 lines of code, like math code. But if you really want to implement it on a drone with all the safety features and checks for unforeseen conditions and circumstances, if you really want to make a Kalman library, it's easily above like 1,000 lines of code. And if you really need to incorporate it into a drone system, we are talking 10,000 lines of code quite easily. Also, feedback control, the very common geometric tracking on SE3 or SO3 controller 10 years ago published by Lee, plus some modal predictive control. These are common techniques which, if you write them in MATLAB or Python, just you would do in like school assignment, you are at 100 lines of code maybe, or let's say 100 lines of math in the language of MATLAB or Python. But if you needed to put it on the drone such that it will fly 100% of the time without crashing the drone and destroying everything you have, then we are talking about 10,000 lines of C++ quite easily. So the system we offer and we use and we have is not only the math, but it's also the implementation, which was not easy to achieve. There was a lot of crashes while developing the system, and we have learned a lot of stuff after the crash happened. But we have also anticipated a lot of problems ourselves, and it wasn't that difficult, hopefully. So what you need to remember when flying with a real drone is that it's not like a simulation. You can crash, and when you crash, you can hurt people, you can destroy the hardware, you can lose your data, which you just recorded in the past 2 hours of experiments. So the easiest way is not to crash. But not to crash, you need to write a lot of routines which will check if the drone itself is actually behaving properly, if all the sensors are connected, if all the data is being transmitted over the wireless, if you actually need the data. So there is a lot of stuff that you should actually think about when deploying software on a drone. And you should basically think about what can go wrong, and anything can go wrong. So our system tries to solve most of these problems which are listed here. Very important problem is not with the drone, but it's with the people. Where are the people? Here, people. When you give your drone to a student or to a person who is supposed to do an experiment with it, don't trust the person. He'll probably try to destroy the drone sooner than you think, just by issuing a wrong command or setting a reference for a controller to some nice number like plus 10 meters in the ceiling. So our system also takes care of protecting the drone from the operators, and you wouldn't believe how often this is actually needed. So most of those problems were already tackled by the system, but since we are doing the video is not playing, that's great. Since we are doing multi-robot systems, and this was a video of a swarm of 14 drones, we are really pushing the limits and we are asking for problems. So imagine you have 14 drones in the air. That's 14 times the probability that something will go wrong. And if a drone goes wild in a swarm, it can easily destroy other drones. So beware with multi-robot systems, there is a new layer of problems coming in. And here I had a nice video of like 20 crashes, which we had in the past 5 years, but you can imagine that, I guess. So back to the math description, or let's say the system description of our system. The first important block which we have in there is feedback control. A lot of people think drones are only about feedback control, that like you need to solve the control problem and you've solved everything. It's not true, but it's a very important part of the system. It keeps the drone moving according to a reference, which is supplied at 100 Hertz. So someone has to give the drone 100 times a second a reference in acceleration, position, velocity, and controllers, feedback controllers, make sure they'll follow it. Currently, we use two approaches for feedback control. One is the SE3 geometric tracking, which we improved slightly 2 years ago. It's all in our big paper on our system. So please, if you can check our paper, everything is down there. Another controller which we use is a modal predictive controller, which we tailored specifically to handle imprecise localization and noisy data. It's important to think for the worst cases. So our system is also designed to handle localization systems which are not that great, which most of the times are the slums, the indoor localization. Outside, GPS, quite fine. We can safely say it's nice out there, but when you fly indoors, data can get nasty, so our MPC can save the drone even when the state estimate and the measurements are not that nice. Another important aspect of the control pipeline is the state estimation and fusion, which takes care of fusing data from all over the localization systems on the drone. And you can have many localization systems running in parallel, and it's useful as a backup. You can have GPS, visual SLAM, LiDAR SLAM, optic flow, 2D SLAM. There's many systems which can run in parallel, and when one fails, another should be capable of replacing the first one. We call it odometry system, but it's more like a state estimation system, is capable of switching from one frame of reference and one SLAM to another frame of reference to another localization system. This is useful when flying from outdoors to indoors through a window, or when flying in a forest, for example, when you might have a GPS system at some field, but suddenly when you fly inside of the forest, you lose the GPS and you can use SLAM instead. So we have a system for state estimation and switching between different localization systems. Another important part of the system is reference tracking, or let's say reference generation. This is responsible for creating smooth and feasible reference for the feedback controllers. And I would even argue that this is the more important part of the control pipeline. This is basically the feed forward. So when you as a user give a drone a reference and you say, let's fly 10 meters there, it's not like you give the controllers a reference which jumps by 10 meters, because that's infeasible. The drone cannot teleport itself. There is supposed to be a system inside which smoothly traverses the reference from point A to point B, given a set of constraints which needs to be satisfied to not destroy the drone. And some drones can fly fast and are quite agile, but some drones are quite heavy and slow, and they can't afford even 2 meters per second squared accelerations. So our system takes care of that, and for each drone we use, we have a set of defined constraints which are always met by we call it MPC tracker, a system for generating smooth and feasible reference. And this tracker, another publication of ours, is able to smoothly track trajectories from users. So if you decide to use the system, you can publish a trajectory into this tracker, and the tracker will follow it smoothly and nicely. And if the trajectory is infeasible and wrong, it will save the drone from crashing, even though you might actually want some infeasible maneuver. So this will optimize the trajectory such that it's actually flyable. And this can also do collision avoidance. If you have multiple drones flying outdoors under the GPS, if you try to collide them, this should make them avoid. And we use this often, and it's quite nice to have if you play with multi-robot systems. So the last and important part of the system right now, I'll skip the videos since they don't play, is the trajectory generation. That's the last member of our core control pipeline. We have added it last year. This is responsible for generating smooth and feasible trajectories out of a series of waypoints. So you as a user might create a path for the drone, which consists of series of waypoints. This trajectory generation will create a trajectory which goes through the waypoints, satisfies the constraints, and makes the drone follow the path nicely. This is not completely our creation. We forked the ETH's MAF trajectory generation. Those two publications are the core of it, and we improved upon the existing parts of the system, and we actually made it sort of usable in the real world. What's important on this system is that our new fork of this is capable of checking its own results against some secondary, let's say, fallback solution. And if the optimization of the trajectory goes wrong, either doesn't finish it at all, which might happen with nonlinear optimization, or if, for example, the solution is infeasible for some reason, for example, for infeasible initial conditions, then we have a fallback solution, and the drone will still fly even though the system sort of breaks. And we have improved upon other aspects such that this can now be used full-time, all the time on the drone. And we successfully used it in DARPA, which you have heard from Martin. We have flew with this trajectory generation in the simulation challenge, where the drone reached 6 meters per second quite often. And thanks to this, or not only thanks to this, but I think this was one of the good aspects of the solution, we have won the $500,000 prize because we were the fastest in the tunnels. So that's the core. We call this the core of the system, which basically takes care of the flight itself. State estimation, control, reference generation, trajectory generation, and all of the safety features around which save the drone if something goes wrong. Implementation-wise, this is actually written as a single program, sort of. Everything is combined into single running binary using nodelets, and there are several managers which handle plugins. Everything is pluginable. So the control part of the system, the feedback control, consists of one set of plugins called controllers. The reference generation part of the system consists of plugins called trackers. We have more of them, not only the MPC tracker. Then we have a plugin which encapsulates everything regarding feedback control and reference generation. And this plugin makes sure that the drone uses the right controller at the right time. And it's very useful when developing new controllers. So if you as a user would like to test your own feedback control, some modal predictive control, for example, you can add your controller in here as additional controller. You can take off with the drone using ours controller. Then you can switch to yours. You can see what it's doing. If it goes wild, the drone can save itself by automatically switching back to ours controller and safely land. This is very useful when testing new stuff which can easily break the drone upon the first iteration. Yeah, and above that, we have some other programs, for example, the constraint manager, which makes sure that the control pipeline knows what is the maximum acceleration and velocity of the drone, because each drone is different. So each drone has these constraints encoded in the system in some config file. So what's again very important is that the system tries to check itself for the errors inside, because you as an operator, as a human, can't possibly know everything what happens inside just by looking at a monitor. So the system typically makes the right decision to end the experiment even before we humans know what's happening. So typically we have a swarm of 15 drones and suddenly one lands. So what happens? What happens? Then we check the logs and we see that the system decided to land because the GPS went wild for 3 seconds and it wouldn't be able to fly anymore, so something like that. Yeah, so this is a full implementation image which you can find on our GitHub. This basically describes every important connection between the nodes, and you could probably find where you wanna, or with which node you want to interact with based on your own setup and desires. So we also provide some additional packages on our GitHub. So not only the core control pipeline, we also provide some modules like sensor drivers, some typical SLAM packages which we forked and slightly improved, like Hector SLAM, Aloam SLAM. We also provide libraries and utilities which might be useful. We typically use Point Cloud library, which we heavily wrapped around, and we utilize that often. And we have our own simulation pipeline, which utilizes Gazebo. And we have a pluginized system for creating, or let's say spawning a drone into the simulation, where you can choose what sensors you want to have on the drone. Just give it an argument. Let's say I want a drone with an OST LiDAR, and the drone will appear there with the LiDAR. You don't have to change files or make changes to the models. It will just, the drone will be glued dynamically together according to your desires. Those are the drones which we typically use in the MRS lab, from the smallest one, which is the F330, F450, this is the Holybro, this is F550, Tarot, and this is the Naki drone. If you desire, you can technically order one of those from our, let's say, friend company. You actually have the link on your beer glass if you forget it. So if you want to do your own experiments with drones, maybe using our system, you can totally replicate what we have in the lab, and you can build your own drones according to our setups. So regarding the MRS UAV system, where are we? It jumped at the end. So the MRS UAV system can be installed in 2 basic ways on your computer or on the drone. The first and traditional installation way is native installation, which I don't recommend right now. Don't do it if you don't have to. This means installing and compiling everything from scratch on your computer. Takes like 2 hours, but you would have everything natively, and you could develop the system, so you could change easily the source codes of the MRS UAV system. You could adapt them. It's useful for me as a developer of the system, but it's not that useful for you because it's hard to maintain, it's hard to update, and it can easily mess up your own computer. Quite nice alternative to this is containers. So we automatically build Docker containers of our system using GitHub. So if you are interested, I can point you to Docker Hub page where you can download our containers. And from those containers, we can build the Singularity image container. Singularity is a container system designed for research. It's slightly better than Docker for the task which we need to do with the system, which is actually run it on our laptops, see the windows, process the data, not only to automate it on the server. So our Singularity is built from our Docker images quite easily, and our Singularity allows you to basically store the system on your computer without huge changes to your computer, and it just eats like 5 gigabytes of space. And you can totally use everything that's in the system, just the source codes are baked in the image, so it's quite hard to change them if you need to change them. We have also flown Singularity on real hardware. It's totally doable. There is no penalty in power, just maybe some slowdown during startup of the applications, but it's totally doable to fly Singularity on real hardware. But you would use this mostly when doing your own research, your own development. Please don't go onto the GitHub and download our Singularity right now, because for you, we have created a special repository, Summer School 2022, which encapsulates Singularity and adds additional scripts which will shield you from the system for now. For now, you don't need to know how to actually interact with our system through ROS, because that's quite complicated and it takes time to learn. So for now, for Summer School 2022, we have prepared a special Singularity image and scripts which will shield you as much as possible from the technicalities. So this is the right time if you want to open some addresses, github.com/c2mrs/summerschool2022. This is a tiny repository, not that huge, but the install script inside will install Singularity. If you have Ubuntu, if you have some other Linux system, please install Singularity yourself according to the official installation guide of Singularity. So that depends on you. If you have Arch, please do it yourself. But when you have Singularity, there is another script which will download a pre-built Singularity image from our servers. If you have Ubuntu, everything should happen automatically using the main installation script. And after everything is ready, you will be presented with a set of scripts which will be there to compile the system. Should take like 20 seconds. To run some lightweight simulation scenario. The script is called run offline. To run the full simulation scenario, this will take some power to run. So if you have powerful computer, good for you. And then there is a script to run PyCharm. Everything you'll do in this task is written in Python. So we have prepared a PyCharm inside Singularity, which actually knows about all the dependencies and will give you code completion and suggestions. So feel free to use PyCharm. Or you could quite easily edit the file on your own computer using your own editor, and then just have the Singularity to run the simulation for you. Everything is possible. More details will be told during a next talk. I'll just focus on the technicalities. But back to our system, if you actually decide to use our system for your own research and development and whatever, you'll need to learn some stuff. And a quick nice guide is given in our MRS cheat sheet. You might have received the cheat sheet in your packages. Good. So this contains all the stuff which I should know, but I don't remember them from top of my head. So I'm using this quite often myself. Using our system requires some knowledge of, let's say, Linux terminal and SSH, and doing those stuff it's quite important to learn the low level of Linux environment. And imagine when you have a drone running somewhere here on the ground. How do you like change stuff on the drone? You don't connect a monitor to it. You need to remotely connect through SSH and then do everything in terminal. So we have prepared a lot of utilities for that. And when we use our system on drones, we use Vim for editing stuff on the drone. We use terminal multiplexer to run multiple sort of virtual windows on the drone where we can see terminal output from different processes. And we use a lot of those low-level Linux stuff. And if you decide to start with our system, you'll probably need to learn some of those because we are quite low level in this. But the cheat sheet should help you, definitely. So if you want this presentation, go to this address on our GitHub. You'll find the PDF there to check the references and the URLs. And this is all from the slides. OK, sure. So, yeah. Yeah. And if we have time, I'll quickly jump to terminal, and I'll show you what you should see when running and downloading the Singularity environment for this summer school task, just to put everybody on the same level of knowing what you should expect. So I'll just mirror the monitors. So if you go to github.com/c2mrs/summer school 2022, for now, this is the only repository you should know about. This is the most important repository, Summer School 2022. It contains a huge README with description of the task. I'll skip it for now. We'll have it on the next lecture. I'll just focus on the installation part of the README. Those of you who are knowledgeable with Git, I recommend to fork this repository, because this repository stores the Python files with the task, so you can make your own changes, you can commit them to your own repository. So I recommend to fork it and make it private, such that other people don't see your solutions. Important. When you fork it, then you clone it on your own computer. That's the part here. I recommend to cloning it into some nice directory like home/git, but it's totally up to you. You can clone it anywhere you want. We use Git folder in home. And after you clone it, the only thing you need to do on Ubuntu or Ubuntu compatible system is to run the install sh script in the repository. This will attempt to install Singularity. It will download our Singularity image from our servers. It will compile the solution, and it will leave you ready for running the task itself. I won't run it now. It takes 5 to 10 minutes to go through the full installation. Typical problems you might see during that is A, you already have the Go language installed, and it will tell you, you have Go installed. Do you want to replace it? If you see this message, it means that you have Go installed, and you probably have different version than we need for our Singularity. Option A is to answer yes, replace the old Go. Option B is to say no. Either way, there is a chance that the Singularity will not be happy during the setup, and you will need to somehow solve this dependency yourself. But you will probably be experienced enough since you already had Go and you have done something with it. Either way, contact me if you need any help. But if the initial installation goes well, Singularity is installed, and our image is downloaded, then you should be pretty ready for opening your terminal, going into the repository, Summer School 2022, and locating simulation folder. And in here, there are scripts which will help you control the environment. One important script is compile, which will compile the sources of the task in the Singularity. And if this goes well, which is the first good sign that the Singularity was installed properly, you will see this output. You'll see some compilation output for something like 6 packages. If this goes well, then you can continue to run the simpler simulation environment with the script run offline sh. This will take some time, but if this opens window of ROS visualizer, we are good to go. So if you are able to get something like this, you are good to go and you can proceed with the task. If you don't see this and if you see any error messages, contact me again and I'll try to solve the problem. These might be quite particular to your system or setup, and it's hard to generally give advice right now. So if you see this, you are good to go, and if you don't, contact me. Yeah. So I think this is enough from me.
Yeah, perfect. I think we have a window for, let's say, 3 questions. So, yeah. Perfect.
Just one curiosity. Which kind of library in C++ do you use for the MPC, for the implementation of the MPC?
So our MPC is written in CVXGen, which is a generator library, so-called. You give it a math description of the problem, and it spits out C code for the solver for that particular problem. CVXGen was developed by Stefan Boyd, I think. Is it? Yeah. And it's quite old for now. It only solves convex optimization, and it's not that fast, but it's reliable enough. I think at one point SpaceX used that on their rockets. And we use it quite happily. It solves the quite complex MPC with 1 to 5 milliseconds of computational time, and it's totally usable. However, nowadays, I would not recommend it. I would probably go for something like Akado or Kasadi, which can totally generate quite nice code. Our MPC is linear, so convex optimization, fast, so that's an easy problem. But yeah.
Thank you.
Thank you so much for the explanation. I want to ask, in the PIXHawk controller, when you connect with the map ROS to the companion computer, how feasible would be to run this code or this system in a custom self-made PIXHawk controller that maybe has a different companion computer, doesn't have all the suite of sensors, maybe it has an RTK GPS but doesn't have a LiDAR?
So totally possible. Our dependency on PIXHawk is quite low, I would say. We only use a fraction of its capabilities for the actual autonomous flight. So the information which we give to PIXHawk is desired attitude rate and thrust, plus some services for arming, disarming, and basically that's all. That's the information which flows from us to PIXHawk. And from PIXHawk to us, we read out IMU, GPS, some state, and barometer, and stuff like that. But we don't rely on the information strictly from PIXHawk. So if we have a GPS receiver connected externally to the NUC computer, we can use it as well. If we have IMU connected to the computer through USB, we can use it as well. So if you would make PIXHawk disappear, we would quite easily change from PIXHawk to another platform. We would just need to supply the attitude rate and thrust to some other platform, either using Mavros or some other protocol. And again, getting data from PIXHawk to us, we are not strictly limited to using PIXHawk. Right now, it's the best platform for the job, but we are not tied to it. It is not that true. Implementation-wise, Mavros is sort of hard-coded in the system right now. So we are dependent on Mavros, and it would take some time to cut it out and swap it for some other system which communicates with PIXHawk. And I have it as a future to do to pluginize this hardware layer. So Mavros would be one of many plugins which you could use for communicating with underlying embedded hardware. But technically, it can be anything like BLHeli, whatever, some other systems. No DJI. DJI is bad. Yeah.
Sorry, and just to continue that line of questioning, is it Arduino Pilot? Is it PX4 Arduino Pilot?
We use PX4, yeah.
PX4, and so the only way to communicate with that low-level system is via it's not possible to, let's say, design a high-level controller that only deals with the waypoints. We have to communicate using thrust and attitude position or values.
So our system can output any command you need. If you need velocity reference, acceleration reference, attitude rate reference, even the motors, we can do it. It just depends what the system on the other side can accept. For flying with custom slums and localizations, you sort of need at least the attitude rate as a reference signal to be able to control the attitude completely yourself. If you rely on PixHawk to control the attitude, PixHawk somehow has to know the heading of the drone. With GPS, it's using magnetometer, but when we are indoors and there is no GPS, PixHawk can't know what's the heading of the drone. So for that, I would recommend going attitude rate, but we can output attitude. That's totally possible. On the other hand, I would not go under attitude rate. I would not go for motor outputs from Nuke because that's quite dangerous. And getting the IMU data into Nuke at 250 Hertz, that's tough job. So attitude rate is the sweet spot of the commands which you can send from the Nuke to the embedded hardware.
Thank you so much.
So we have a room for last MRS system question. If you have a question about the task, it will be later on. So I had first hand there.
So a question is, so in the block diagram, it is mentioned like this onboard computer and the PixHawk are communicating using UART communication protocol. So what would be the rate of this protocol? I mean, how much hertz?
So currently we are at 1 megabaud per second communication between megabaud or megabit per second between PixHawk and the Nuke.
So and it is consistent, or some samples are dropping? I mean,
sorry, I didn't understand.
it's a consistent communication, or the samples are dropping while the
No,
during flight?
nothing is dropping out of that communication. However, we had to tailor what we actually want to get from PixHawk. So some stuff are sent at 100 Hertz, like IMU, attitude. Yeah, the important data are sent at 100 Hertz, but some which are not that flight critical are degraded to 10 Hertz or similar. So we had to tailor the configuration for PixHawk such that it goes through the 1 megabit per second regular or reliably. Yeah.
I see. Okay.
Yeah, don't worry. You can ask other questions throughout the week. I'll be here the whole time, even during the labs. So reach me if you want, or over the Slack, of course.
Yeah, perfect. That was exactly what I wanted to say. Yeah. So